That reflects my background. I work in a school of medicine at UCLA. Thank you. And these problems are motivated by big data analysis. I'm going to be talking about optimization methods for analyzing big data. And I first want to introduce a generic technique that stands behind the more particular proximal distance class of algorithms I'll mention later. I've named this class of algorithms. I don't know if that will hold up over time, but what stands behind it are these algorithms, and they're for both maximization and minimization. If you want to minimize, then you majorize, and then you minimize, and if you want to maximize, you minorize, and then you maximize. And the whole idea is you create a surrogate function for the function, the objective function you want to optimize. And the surrogate function is designed to be simpler to optimize. And when you optimize it, it sends the objective function downhill or uphill, depending on the circumstances. So these are monotone algorithms. They're tailored to these high-dimensional problems in data mining and statistics. And this celebrated class of EM algorithms in statistics are special cases of algorithms. I've listed some places to read about the algorithms. I'll pass over those, show a slide at the end. Let me just give you a little bit of a history. The idea of particular algorithms appeared very early on. Earliest I can trace back is to 1927, a paper on estimation of infection rates. Then there's something called Weisfeld's algorithm for the Fermat-Weber problem from the 30s. The principle was enunciated clearly for the first time in the numerical analysis book of Ortega and Reinbold in the context of one-dimensional searches. Now, the modern development started with the EM algorithm in 1977. The Dempster, Laird, and Rubin paper it may be at this point the most cited paper in statistics. It has nearly 40,000 Google citations. There was a companion paper which was largely overlooked that actually dealt with the more general principle, and it currently has 305 Google citations. But one algorithm is a subclass of the other. It says something about the writing ability or presentation of the material. The principle has many applications. It's been recognized and used implicitly in large numbers of algorithms, projected in proximal gradient algorithms, and it comes up in interior point algorithms, robust and quantile regression. I've used it in discriminant analysis, medical imaging, non-negative matrix factorizations, matrix completion, so on and so forth. So there's a wide class of algorithms that have this at its basis. So here's a general idea. You take a function you want to minimize and you majorize it by a surrogate function, we'll call it G, and that involves two conditions, a tangency condition, so your tangent at the current iterate of your iteration process, and a domination condition, which are shown on the slide. And the whole idea is to choose a good majorizing function, and if you minimize that majorizing function, which serves as a surrogate for the objective function, then you get the next point in the algorithm, and it drives the objective function downhill. And this descent property is shown on the bottom of the slide. And the descent property flows directly from the definitions, from the tangency condition, the domination condition, and the definition of the next iterate. And you simply now iterate until convergence. If you minorize, so you're putting the function below instead of above the objective function, then you get an ascent algorithm rather than a descent algorithm. You can connect this with Lyapunov functions. You encounter these in difference and differential equations, and the Lyapunov function decreases along a solution trajectory. In the MM algorithm, you kind of turn things around, so your objective function serves as a Lyapunov function, and the problem becomes one of constructing the solution trajectory rather than the Lyapunov function. Now, if you view it from the point of view of differential equations, you can come up with a continuous version of these MM algorithms, and I've given that middle equation. It's a differential equation you can solve, and along the solution curve, if the surrogate function g is strictly convex, then you can show, and I've shown here in the bottom inequality, that this solution decreases the objective function. And this has a practical importance that you don't actually have to solve for the next iterate exactly. You can solve approximately, and if you use one step in Newton's method, you have the same local rate of convergence as if you solved exactly. So that's kind of a nice perspective on it. Here's a diagram of majorization. This is the simplest possible context. This is just the cosine function. I've got a couple of points there, and I've got quadratics that hug the cosine function and sit above it. And you can see that on the green and the blue curves, you just move to the bottom of those curves, and that gives you your next iterate. Okay, so what are some of the reasons for using this principle for designing algorithms? Well, if you think of the EM context, EM stands for expectation maximization. It frees algorithm derivation from the hidden data straitjacket that's part of the EM algorithm. More importantly, you can separate the parameters of a problem and thereby avoid things like matrix inversions if you used Newton's method. So it's perfect for massive parallelization problems. You can linearize an optimization problem by creating a quadratic surrogate, and I'll show you one in a moment. You can restore the symmetry and deal gracefully with constraints, and you can deal with a whole classes of non-differentiable problems. So there's quite a few good reasons for passing to this paradigm. How do you majorize or minorize functions? You just use the classical inequalities that we've all learned in undergraduate calculus or analysis. Jensen's inequality implies the information inequality, which is the basis of the EM algorithm. The Cauchy-Schwarz inequality was used by Jan de Leeuw in his early paper on stress majorization and the arithmetic geometric mean inequality. You can use that, for example, in geometric programming. Convexity enters in a big way through the supporting hyperplane property. That gives you a minorization. And if you want a majorization, you can use the quadratic upper bound principle, which says you need some kind of bound on the curvature of the objective function. So you want to replace the Hessian of the objective function by a matrix which is more positive definite than the Hessian is. Okay, let's go back to our trivial example of the cosine function. I'm trying to make this very didactic. So if you take a second order Taylor's expansion of the cosine function, you can replace the quadratic term, you can replace the second derivative of the cosine by 1. It's always bounded above by 1. And you get a majorizing function. Now, if you set the derivative of that majorizing function equal to 0, then you get an iteration formula. xm plus 1 equals xm plus sine of xm. Okay, now this was an interesting trivial example because it illustrated a point that I wasn't aware of, and that is, in some cases, you actually get quadratic convergence for these algorithms. By and large, you only get linear convergence, and in some cases, you only get sublinear convergence. But for the this particular simple example, here are the iterates for this finding the minimum of the cosine, and MM actually beats Newton's method. I think what happens is Newton's method tends to overshoot a bit and takes a little longer to catch up. But this illustrates the point: if you want to have a successful MM algorithm, you need to hug the objective function as tightly as possible. Okay, now to talk about these proximal distance algorithms, I want to introduce two concepts that are familiar to anyone who studied convex analysis. One is the proximal map, and it basically takes an objective function f of x, adds a spherical quadratic perturbation to it, and then takes the minimum of that. And the place where that minimum occurs is the proximal map of f. Now, a special case of that proximal map is a projection map, where this function f is replaced by a convex indicator, which is 0 off a set, on a set, and is infinite off the set. And then in that case, the projection is taking an exterior point to the closest point on your closed set. Now, when people do projections and proximal operators, they almost always do it in the context of convexity. And it turns out that it's useful to deal with non-convex functions and non-convex sets. What you give up is, if you project onto a non-convex set, you may not have a unique projection. But if you can still define a projection operator, just maybe multi-valued. Okay, let me give you a couple of examples, classical examples of how you could construct an MM algorithm, and these come from projections onto sets. So I define here the distance from an external point to a set S, and that's obtained by, at the projected point, upper equation, p sub s of x, and you get a nice majorization with that projection function. So if xn is your current point, then the distance from x to s is majorized by the Euclidean distance between x and the projection of the current iterate. Okay, so if you want to find a point in the intersection of two closed sets, what you can do is you can set up an objective function which is the sum of the squares of the distances to the two sets. And if you majorize using the Euclidean majorizations, now it's trivial to solve for the solution. And the solution simply is you average the projection onto S with the projection onto T, the two sets you want to project onto. And this is not new material, it's very classical, but what's interesting is you can motivate it from this MM perspective. You can quote, derive the algorithm. You can't derive all the properties of the algorithm, but you can give a principled derivation of the algorithm. If you want to look at alternating projection, you can do the same thing. So you have two closed sets, S and T. Now your objective function is the distance from x to t, but we're going to do constrained optimization, so it's subject to x being in S. So we want to minimize that distance subject to x being in S. We have a surrogate function, again, which is a Euclidean distance now to the set t from the current iterate. That majorizes the function. Now it equals the function of the objective function when x equals xn, and it dominates it otherwise. So it's a nice majorization. And the minimum of the surrogate function, subject to x being in the set S now, occurs Well, you just take the projection of the projected point onto T, you take its projection onto S. And you get the alternating projection formula, which dates back to von Neumann. He studied it in the context of affine subspaces, and it's very well worked out there. But the connection, I don't think, has always been drawn to this class of algorithms. Okay, now this brings me to the important part of the talk, the new material. So I've been reading over a period of years a book which I consider rather difficult by Borwein and Lewis on convex analysis, and I work problems. It's one of the authors here in the audience. Hello. So I worked problems on the bus going to and from work, and I finally got to the chapter, I think it's on tangent spaces or something, I don't know, tangent vectors. And here was Francis Clark's exact penalty method. So Francis Clark showed that you can convert a constrained optimization problem into an unconstrained optimization problem. You replace the objective function f by f plus a constant times the distance from x to the constraint set. And you get the same global optimum, same global minimum. You can extend this result to Lipschitz functions if you substitute local for global minimum. And you can also substitute a function, a substitute for the distance function. It has to be 0 on the set S, the substitute function, and it has to be above the distance function, at least scaled by a constant. Okay, so the question popped in my mind as I was trying to read through this material was, how can I convert this exact penalty method into a workable practical algorithm? Because the distance function itself is a somewhat nasty object. It's, for example, not necessarily differentiable. Okay, so the rest of the talk has to do with how I approach this problem. I don't claim it's the only way, but it leads to interesting results. Okay, so the first thing I suggest doing is to approximate the penalty term. And I want to approximate the penalty term by something that's closely related, involves the square of the distance, because the square of the distance is differentiable even though the distance function itself is not. So, the double inequalities here show that this square root of the distance squared plus a small epsilon satisfies these bounds and should be close to the distance function for epsilon small. That's just obvious. Okay, so the first thing is we substitute for the distance function this smooth version. Okay, now if the Clark's function is coercive and achieves a unique minimum, then you can argue that the solutions to these proximate problems converge to the solution of Clark's original problem as epsilon goes to 0. So if we take a very small epsilon or a sequence of epsilons tending to 0, we may recover the solution to Clark's problem, which is this constrained optimization problem. Okay, the next step is to majorize the approximate problem. And we majorize the distance function squared by this Euclidean distance from x to the current projection. Okay, that's the first majorization. And the second majorization is a linear majorization of a concave function. So we're placing a line above a nice concave function, which is the square root of t plus epsilon. And I show in the middle of the slide this linear majorization. And if you substitute for t the Euclidean distance squared, you come down to the bottom inequality, where I've collected the garbage into this constant Cn, which may depend on the current iterate, but does not depend on the next iterate. So the right-hand side of that bottom inequality now gives us a surrogate function which we can minimize and drive the approximation to Clark's exact penalty function downhill. Okay, so I've repeated it on this slide. We now have a function to operate on, and you'll notice that it's set up exactly to be solved by one of these proximal operators. And the reason I thought bringing in the proximal operators was useful is because there's this huge body of knowledge about proximal maps, many of them exact results, and many algorithms which are very fast that you can use in high dimensions to solve proximal operators. And I just mentioned that the algorithm is guaranteed to decrease the objective function. So you can also, I should point out, you can, in the process, you can majorize the objective function as well as the distance function. The sum of two majorizations is a majorization. And for example, you can try to separate the parameters of the objective function. And if you do that, what you get down to is the proximal problem parameter separates, and you can solve for all the components of the parameter vector component by component. And you can do this for convex problems very quickly by an extension of the standard bisection algorithm. Okay, now, so what do we do in practice? Well, in practice we take our penalty constant rho, which, and I don't know if I said it, but rho has to exceed the Lipschitz constant of the objective function. So there's some kind of controlled behavior of the objective function. It doesn't have to be convex, but it has to be at least locally Lipschitz. So we take rho slowly up, and we take epsilon slowly down. And as I said, this works in practice. I don't have full validation, theoretical validation for this, but if you take these things slowly, like alpha equal to 1.2 or even 1.1, beta equal to the reciprocal of that, then you get good behavior in many problems. Of course, if you can find a global Lipschitz constant and plug it in here, it is very useful. Otherwise, rho is going to tend off to infinity, and you spend too much energy and too much time fitting the constraints rather than the function. Okay, here's a typical example. Binary piecewise linear function, non-differentiable. You want to minimize this subject to the components of x being 0 or 1. So you have a discrete set. It's closed, but it's not convex. This arises in graph cuts. You can compute a Lipschitz constant for this problem. I put it on the slide. And the interesting thing is you can majorize the objective function, so you separate the parameters. And the bottom equation here shows the majorization to use to separate the parameters. And by separating the parameters, you turn this into a problem where you can update each component separately. So it's very fast. There's no linear algebra. And finally, to make this work, you have to project onto this discrete set. Well, that's trivial because every component of x, you just round to either 0 or 1, depending which is closer. Okay, so here's a comparison on problems of various dimension using this algorithm versus CVX, which is a standard convex solver coming out of Stanford, Stephen Boyd and Grant. And this algorithm does extremely well, even on high dimensional problems, whereas CVX begins to choke. Now, I'm not slamming that piece of software. It's a lovely piece of software, but the way it attacks the problem is hardly optimal here. Okay, here's a more pertinent problem in statistics. It's regression with an L0 constraint. L0 means you're trying to limit the number of regression coefficients that enter the model. So we have a standard least squares model. Y is the response vector, X is the design matrix, beta is the regression coefficient. We have to, the constraint set consists of those betas, those regression coefficient vectors, with at most k non-zero entries. So we want to solve least squares problems with exactly k predictors entering the model. And if we want to project onto this set, which again is not convex, but it is closed, we just zero out all the coordinates except those k with the largest absolute values. Now, there can be ties in practice, but usually there are not. So what does the proximal distance algorithm do? It minimizes now this convex quadratic, and this turns out to be far more efficient than searching through all subsets of size k. That's a disaster because of the large number, astronomical number of subsets. And this, in our hands, is more effective than the lasso because the lasso has strong shrinkage and it often delivers a surplus of false positives. I'm not claiming the algorithm is as fast as the lasso. Here's some results. 100 simulations average. You can see the problem size. N is the number of cases. P is the number of parameters. I've got the number of true predictors recovered by the two algorithms out of 10 predictors. And this proximal distance algorithm does better than the lasso in that respect. It also produces a better loss function. The loss function is lower, so it's giving a better fit because it doesn't shrink. And the compute times, well, it's really hard to beat the lasso, and it doesn't beat the lasso here. But I would argue that if it gives a better solution, maybe you should at least consider it then versus the lasso. Of course, there are many competitors to the lasso now, and they probably would do much better than what I'm showing here. Okay, here's another class of problems, matrix completion, introduced by Candies and Reich. Emmanuel is sitting here in the audience. So you're given a matrix partially observed. Many of the entries are missing. You want to fit a matrix X to your partially observed matrix Y, so you have a sum of squares criterion over the observed entries. And you want to do this subject to some kind of rank constraint, and you can introduce that as a penalty, and what's usually done is that enters as a nuclear norm penalty. If you majorize, you can fill in the missing entries. So you majorize by replacing the missing entries by their currently predicted values. This gives a nice symmetrization of the problem. So Z is either equal to the observed entry or the current predicted entry. Okay, now rather than add a nuclear norm penalty, you can project onto the set of matrices of rank k or less. Now how do you do that? Well, it's standard knowledge that you take the singular value decomposition and you just truncate the decomposition after k terms. Okay, so the proximal distance algorithm minimizes this criteria in the middle here. It's a simple least squares problem, and the solution turns out to be Zn, your current imputation, your current combination of the data and the imputation of the missing entries with the projection of your current estimate, Xn. So it's a nice convex combination depending on these weights. Here's some data on performance. P is the matrix is P by Q, so we've taken it up to 5,000 by 5,000. Alpha is the percentage of missing entries. The rank is given in the fourth column. And the losses achieved by the nuclear norm penalty, and this is in a program called Soft Impute by Hasty and Zoomer. You see that you get much better loss under the proximal distance method. And the timing favors the soft impute, but on large problems, the times there's not much difference. It's about twice as much time to do this proximal distance algorithm as it takes to do the standard method. So I would argue, again, in this case, you're seeing better results for approximately the same amount of computation. Okay, so what do you do if you have multiple constraint sets? So you may have multiple sets. You can project onto each one of them easily, but you can't project onto their intersection very easily. Well, now you can use one of these substitute distance functions, and the one that works best in practice is the square root of the sum of the distances squared. Go back, use that in Clark's exact penalty method. Now this, you have to invoke a hypothesis called metric linearity here. So difficult topic in convex analysis and non-convex analysis. I'm not going to enter into it. There's a lot of research interest in it now. Local linear regularity, let me mention, is probably more relevant than global linear regularity. Okay, so how do you modify the proximal distance algorithm when you have multiple constraint sets? Well, now you have, again, a weight. The appropriate weight is, appropriate weight is down here in the middle. And you have a sum of these Euclidean distances from the projections under the different subsets. You can summarize that as a spherical deviation from the average projection. Cn here is an irrelevant constant. So if you minimize this function, then you drive f of x downhill. As long as your constant rho is above the Lipschitz constant or a local Lipschitz constant for f of x. So we tried this on the simplest problem, but one that's applied probably more often in mathematics than any other, computational mathematics, linear program. I wanted to see how it worked. It's a very simple objective function with a Lipschitz constant that's given by the Euclidean norm of the vector c entering in the objective function. The constraint sets are non-negativity and bunch of linear equations. You can project easily onto the non-negative orthon very easily. You can project onto the linear equations by standard linear algebra techniques. And what you need to do, and this is the part of the algorithm that takes the most time, is compute this projection. So we compute this inverse once and store it and use it repeatedly. Here's the objective function, the surrogate function, I mean. And when you minimize it, you get this update. Involves two projections, an average of two projections, and then a perturbation by the function defining the linear programming problem. And at this stage, there's just vector operations and matrix times vector multiplications. So very straightforward. And here's some solution times. So two equations, number of variables, number of constraints. We tried not only CBX, but we programmed this all in MATLAB, and we used two commercial solvers, the one in MATLAB and the one in a different one. And to our surprise, this was at least an order of magnitude faster than the commercial solvers on these medium-sized problems. I haven't tried truly huge problems yet, but I thought this was an interesting test case. You can also use this method for projection onto the intersection of sets. And I advocate using this objective function rather than the norm squared itself, because this objective function is actually Lipschitz, and it has a Lipschitz constant of 1. And when you solve for the updates, they're a convex combination of your external point y and the average of the projections. This alpha is unknown, so you have to solve for that. And you do that by setting up standard stationarity conditions, and it's basically a one-dimensional problem that's straightforward to solve. I won't go through the details. And I tried it on the simplest problem, closed ball intersected with closed half space. It does about as well as Dijkstra's algorithm. I'm curious to see how this will do on higher dimensional problems. That's not a spectacular result. It at least works. You can use this method to project on, find the closest correlation matrix. This was a problem that received a lot of attention in numerical analysis literature. Or the closest positive semi-definite matrix with non-negative entries. All you have to do is be able to project on these spaces, and it's straightforward to do this. And I tried an example, 100 by 100 random matrix. It took about 100 iterations to get to the closest correlation matrix. Okay, so what are the conclusions from this? The proximal distance principle offers a new perspective on constrained optimization. It capitalizes on this principle and Clark's exact penalty method. And it should scale to fairly large-scale problems. I put on the middle line again what the algorithm is doing. It's just projection and a proximal map. The convergence theory is complicated because you're multiplying the objective function by a constant, this weight function, this weight Wn, which changes from iteration to iteration. So trying to show that you have, say, a non-expansive map gets messed up here. The initial results on this algorithm, I think, are quite encouraging on sparse high-dimensional problems, even non-convex problems like the L0 regression problem. On low-dimensional problems, such as the 8 queens problem, it didn't work well. These are problems that have too much combinatorial complexity. The high-dimensional problems in data mining don't have as much. The problem is the dimensionality, not the combinatorial complexity. The proximal distance algorithms tend to improve versus the competition. This is just a practical observation as the problem size increases. We've tried this, and I don't have time to talk about it, on convex cluster analysis, a new way of doing cluster analysis, sparse covariance and precision matrix estimation, sparse regression models with generalized linear models, and in genetics, haplotype reconstruction and genotype imputation. Also, this should be applicable in medical imaging. So what do we need at this point? We need further experiments, and we need better theory to understand the potential and limitations of this new class of algorithms. So what are some of the open questions? Well, I can prove that the algorithms, at least in the presence of convexity, converge. I cannot prove how rapidly they converge. I don't have any local convergence rates, and I don't have any computational complexity rates. I don't have proof that if I simultaneously take the penalty parameters up and down, that it works. If we fix those parameters, then the global convergence theory works. If we gradually move them, I'm not sure what happens, but it works in practice. So there are a lot of theory problems, and I hope maybe some of you will get interested in these and contribute to our understanding. There's still a lot of potential applications, still a lot of testing to be done to make sure that this is a viable method. Identifying these Lipschitz constants is quite helpful. I found recently that what I did for the projection on the intersection of sets, you can extend that to any quadratic function. So you generate, by doing that, a universal Lipschitz constant. It's not just local Lipschitz, but you have an easy, well-defined global constant. And you can write parallel code for these kind of applications. You can use graphics processing units. You can use multiple cores on computers. I don't have time, but there's also ways of accelerating the algorithms which can make a big difference in practice. I think I'll just show some references if you want to pursue the MM algorithm in more detail. My conference proceedings, my contribution, expands on the notes on this talk. And I'll stop there.
So, any questions, comments? Okay.
Perhaps in your linear program example, so people who solve linear programs, they also want to have feasible solutions. So obeying Ax equals B and X non-negative.
Mm-hmm.
Whereas the algorithm you presented, you're never really feasible. You become, in the end,
Right.
feasible. But so when you show your table and where you're stopping, one criterion people would like to see is distance to feasibility. How far are you from actually being an actionable solution that I could?
Well, in some sense, you have that immediately from the projections themselves.
I don't think, no, because it takes a sum, right? So PS of X plus PT.
Yes,
no.
Well, you have
So you
distance.
want X and non-negative, but at every iteration, some components of X might actually be negative.
Yes. Okay.
And so if we're recommending a diet or something,
Yes.
I cannot have negative intake of it.
Yes, these are definitely exterior point methods. They're not interior. You're not always feasible, just in the limit. You-
So, let me give this present to our speaker, and thanks the speaker.